All right, hopefully people can hear me. I will start. I see a lot of new names, which is kind of cool. So yeah, welcome everyone to a new semester of Sigma. Um, Glad you guys could be here, and I'm hoping that um, you know, this is my last semester doing this, so hopefully this can be a good semester. So yeah, without further ado, first I'm going to introduce the other admins, and then I'm going to introduce people to the P versus NP problem. You might have seen it before, you might not have, um, but kind of just lay a good foundation. And then I'm going to introduce you guys to a new type of circuit. So not electrical circuits like you might have seen, or with like and OR gates, but more algebraic circuits, which don't really come up in other courses. So hopefully it's new to everyone. And then I'm going to apply it to do a really cool parallel algorithm for a very foundational problem in computer science. So yeah, just a couple updates about the club. So first of all, we are back. Yay. Um, there are two channels I want to point to people in the Discord. So if you haven't joined the Discord already, if you just go to cstheory.org/Discord, then you will be able to join the Discord. But I also don't know how you would have found the Zoom link if you're not in the Discord. But there's two channels, research advice and seminars. I kind of hope people make use of this. I want people to push the stuff. I would love to see more people in the server doing research. I think that's one of the coolest things you could do. And I'd like to see more people going to seminars. And yeah, I'll talk shortly about how you can come and make meetings for Sigma. We have a couple slots left, but I'm already seeing some new people make meetings for us throughout this semester, which is going to be really cool. But yeah, first, let's introduce the admins.
Hello, I'm Sam. I'm here now doing a CS PhD, but I've been working with computational geometry and as well as fine-grained algorithms with Sariel and Timothy. I'm also involved with Sigma for Security. I'll be giving a meeting sometime in March.
Hello, my name is Hassan. I'm just a CS major. I'm graduating this semester. I'm also involved in SigPony, as well as I'm the ACM infra lead, although I'm stepping down to that position pretty soon. I help CA CS341 and CS173 if you've taken those classes. And since my freshman year, basically, I've been doing compiler research, working on one really big project that's finally been published as a paper in a pretty nice journal. And like I mentioned, this semester I'm graduating and going to sell out in industry.
Okay, I don't see Ryan, so I'll talk his behalf. Ryan's super cool. So he's a junior in CS and he's a CA for the three classes, God. 222, 374, and 461. Um, his interests have always been kind of like the like probabilistic side, but he's also interested in game theory and like fair division kind of stuff. And he's working on approximation algorithms for your fair division. Um, I'd imagine that's with Ruta, but I'm not exactly sure. And he's doing some hardware stuff as well, which hopefully he can talk about soon. It's really cool stuff.
Hi, I'm Alex. I'm stat and CS and double majoring in math. For research, I'm part of the People Weave project, which is focused on improving research recommendations. I'm also in the talks for starting compilers research for data science/ML. So hopefully that works out. I'm a CA for 225 and 374, and I'm totally a foosball pro.
Hi, I'm Porter. I'm a sophomore CS major and math minor because I kind of discovered that I like math since I got here. I was intern at CDK Global over the summer, and I'm going back this summer. It's a car dealership software company. Um, I'm a CA for CS 128 honors, and like Alex, I'm a professional foosball player. So if anyone wants to play me.
All right. And then, hi, I'm Anakin. I'm kind of the president of Sigma. I'm currently doing like some more combinatorics type research with Alexander Young, but I used to do like I've done some computational group theory stuff. I used to do graph theory and optimization research with Sam. I'm happy to talk to anyone about any and all of this stuff. I also do stuff with the Sig Pony, multi-cryptography stuff. And I also run Coffee Club. Come out to Coffee Club. Ask me more about it. It's great. And then you might have seen me CA like some of the more theory type courses. I guess brand new is I'm seeing 225 honors with Jeff, so that'll be super cool. But yeah, I promised everyone an opportunity to make meetings. So hopefully this can be an opportunity to get some new faces into the club. So I kind of came up with this idea. I stole it from the Waterloo version of this club. So I'm calling it the short and sweet presentations. And so what I'm envisioning is that these are going to be 3 short presentations, about 10 to 15 minutes long. Hopefully I'll also have like some food and drink to kind of make it a little bit more fun and relaxed. I'm holding these on 2 days, March 18th to April 22nd. You might have seen an announcement before. And the idea is I want people to kind of come up with a shorter presentation presenting maybe like an easier topic. It's like more low level, kind of a cute little idea. You don't have to develop it over 30, 40 minutes. Because I know making a longer meeting can be kind of daunting for people. So hopefully these shorter meetings are a little bit more tangible. So it's a good way to show that you're interested in the club if you're interested in becoming a future admin. But yeah, DM any of the admins if you are interested. This is the same thing I was talking about in some of the earlier announcements if you've been in the Discord for a while. But yeah, I'd love to see some new faces give meetings. I think it's a really good skill to have, and it's also I like learning about new things. A lot of the meetings that other people give, I basically learn something new, so it's a good way. And if you have something interesting you want to talk about, it's the perfect way to do it. Yeah. Um, Without any further hesitation, let's talk about P versus NP, the $1 million question. So one of the biggest ideas in computer science are these things called complexity classes. And you can broadly think of these as like groups of problems which are characterized as being of similar difficulty, like all the easy problems or all the hard problems for whatever easy and hard mean. Typically when we think about difficulty, we think about kind of like the running time. Like if I give you an input of size n, how long does it take to compute the answer? And we think about like the algorithms that solve these problems and how long do they take to run. So like if we say an algorithm runs in big O of n squared time, then that means as n tends to infinity, the algorithm takes c n squared time for some constant c. So it kind of grows quadratically, or these could be logarithmically or whatever. So this is kind of how we measure difficulty in computer science. And typically, we think about 2 broad classes of problems, the quote-unquote quick problems that take polynomial time to solve, and then the problems that require larger than polynomial time algorithms to solve them. So they require exponential algorithms or factorial algorithms, or maybe even worse. So these are the easy problems and the hard problems. And even more specifically, a lot of the core problems of computer science are kind of just yes or no questions, which we call decision problems. So some classic examples are like checking if a list is sorted, as opposed to actually sorting the list. We're just checking if the list is already sorted or not. We can check if a graph has a path that visits every node exactly once, and we can ask if a number is prime. These are all yes or no questions. And typically, the computation model is a Turing machine, which for all intents and purposes is a computer as you know it, written in your favorite programming language. If you've never seen Turing machines before, this is a good enough approximation, unless, for example, your favorite programming language is HTML for some reason. That's not Turing complete as far as I know, but most normal programming languages are. And like I said, these are all like we're defining a problem. We need like some sort of sense of the size of the input. So kind of building off the previous questions, we can ask is a list of length n sorted? Does this graph with n nodes have a path visiting every node exactly once? Or is this n-bit binary number a prime number? So we have some notion of the size of the problem, and this allows us to talk about the complexity, like I said earlier. And really the two big paradigms we're talking about these decision problems is solving the problem and verifying a solution. So we could consider the problem of finding finding a path in a graph with n nodes, and we can check if one exists. And so solving this problem would take like a really long time. There's like n factorial orderings of these nodes. And so this is solving the problem. And for this example, right, this algorithm I gave, just trying all of them brute force, takes n factorial time. But also, there's the idea of verifying the solution, where if you claim to have solved the problem, saying, hey, here's a graph and here's a Hamiltonian path, I can check that really easily because you've already given me a solution. I don't need to find a solution. I just need to check if that solution is correct or not. So we have solving a problem and we have verifying a problem. And we can ask like, what are the relative difficulties of these? In this example, it seems like the difficulty, at least with these two algorithms I gave, it seems like the difficulties are pretty far apart. And that question is exactly what was posed by the Clay Mathematical Institute in the year 2000. They posed the Millennium Prize problems, a total of 7 problems. And the whole catch was if you solved one of these problems, you would get $1 million. And so the P versus NP problem asks about whether the two following complexity classes are equal. So we have P, which is the set of all decision problems with polynomial time algorithms which solve the problem. So this is I can solve the problem in polynomial time, where NP is the same, except instead of solving, we're asking what can we verify a solution in polynomial time. So the previous example we gave about the Hamiltonian path visiting every single node in a graph exactly once, that's an NP, because I said like if you give me the problem, the solution, I can just check in order that path, whether it visits every node or not. And so these are the two complexity classes, and we're asking, are these the same? Is solving a problem around the same difficulty as verifying if a solution exists? So any questions about that? Do we kind of get the big picture idea what P versus NP is? All right. So we were just talking about a computational model in terms of a normal computer, like a computer that we use every day with your favorite programming language. We're talking about these decision problems. But there's a very like pure mathematical version of these, and the computational model is what's called an algebraic circuit. So what is an algebraic circuit? So these were introduced by Valiant in the year 1979, and these are introduced as like algebraic equivalents of the P versus NP problem. And in the more recent decades after this paper came out, there have been a couple computer scientists, namely Mulmui at U Chicago and Sohini, who's at one of the IITs in India. They've been furthering this approach, and it's currently being seen as the most viable approach to actually resolving P versus NP. But what does this actually look like? So the idea is now instead of talking about computers and programming languages, polynomials are going to be our computational model. So these are polynomials like you've seen in every single like math class, right? Just your normal like x squared plus y or like 2x squared, whatever. Just normal polynomials are going to be our computational model. And we can model them using what's called a circuit. So you can see up above, we have like this polynomial x to the fourth minus 4x cubed, blah, blah, blah. And I've also factored it on the right-hand side. And if you think about it, like a polynomial is almost like a instruction for how to compute a value, right? You can plug in a number for X and it tells you apply these steps, right, in terms of order of operations to compute the value. So we can see on this circuit, so these circles with the straight X, this is multiplication. And so we can see the leftmost node has the variable X at the bottom going up into this node on the left, and that represents the X to the 4. I made a mistake here. That should be it. Whatever. And then you have this node just to the right of it with the 2 and then the X going into it 3 times. That 2 should be a -4. My bad. But that would be, in theory, the minus X minus 4X cubed. And then, we have a 2X squared, and then we have 4X, and then we have a -3. And then they all go into the summation gate at the top. And then there's that top gate's kind of the output. So at the bottom, we have the input X, and at the top, we have the output of that summation gate. And it kind of represents a circuit for computing this polynomial. But it's not the only circuit we could draw. We have this factored version on the right-hand side, and we can see that if we take X and -1 and we sum them up, we throw it into a multiplication gate, we get X minus 1 squared. And then we have another one where we take X and 1, sum it up, throw that into a multiplication gate, and then X minus 3, sum it up, and then we throw all of those into this top multiplication gate, and that gives us the factored form of the polynomial. And so we've kind of established that there's a computational model for evaluating polynomials. And this is like the algebraic version of computation. So hopefully that makes sense. Sorry for the mistake with the X cubed gate. I will fix that later. But in terms of computational complexity, right? So before we kind of had this big O notation, but there's no like code running here. So we need like a different measure of complexity, because we're not saying, oh, here we have a algorithm. You can run it on a computer and it takes big O of n squared time to run or whatever. But so what could be the measure of complexity? And there are really 2 things we could think about. So we can think about the number of nodes in the graph, in the circuit. So like including all operations and all like constants and whatever. So the number of nodes, and this is typically called the size. And then we could also think about the depth. So how long does it take to go from the input at the bottom to the output gate at the very top? Like what's the longest path? And that would be another notion of size, right? And there's a lot of like size and depth trade-offs that one could play with. Especially like there's a lot of variations on this kind of computational model. And then so given some random polynomial f, we can ask kind of 2 types of questions. So can we construct a circuit for f with small size or depth? And then similarly, can we show that no such small circuit for f exists? So like no matter how clever you are, certain polynomials are so complicated that they need circuits of a certain size. You can't get any smaller. So these are kind of the 2 types of questions we ask in algebraic complexity. And so we have P versus NP, right? So P, right, the decision problems we can solve in polynomial time. NP, the decision problems where we can verify a solution in polynomial time. And then it should be intuitive that if you can solve it in polynomial time, well, then you can verify the solution in polynomial time, right? You can just run your verification can just check, like, because intuitively verifying should be at most as hard as solving it. So P is a subset of NP, and most people believe it's a proper subset. But so that's the $1 million question from the Clay Institute. And then so we can ask the algebraic version. And these are what we call variance P and variance NP, or VP and VNP for short. And so we have a polynomial f of degree, let's say d. Let's just say poly d. So VP asks if f has a polynomial, has a poly-sized circuit to compute it. So does there exist a circuit which is polynomial in the size of d, not n, my bad, to compute it? So does a small circuit exist? Polynomial size is typically considered small. VNP just says, can we look up terms in the polynomial and find its coefficient? So if you think back to the first example, if you gave me that polynomial, right, there's probably a circuit out there where you can give me the term x to the fourth, and I can tell you, oh, the coefficient of x to the fourth in my polynomial is 1, and the coefficient of like x to the fifth is 0, and the coefficient of x cubed was -4. So instead of instead of computing the whole polynomial, the way we're verifying it is we can ask about coefficients of certain terms. And then so the question is, so then we have that VP is a subset of VNP. Because if we can compute the whole polynomial, then we can kind of expand the computation and just look at the coefficients. And then there is the question is the reverse direction true? Is VNP a subset of VP, or is VP a strict subset of VNP? And so that's kind of like the algebraic million-dollar question. And so we can think about two polynomials that you're probably familiar with the first one, the determinant. So what is the determinant? Like, you've seen this for a matrix. You kind of expand it recursively. So if you have an n by n matrix, right, you have this alternating sign, and then you take a term, and then you recursively compute the determinant after cutting out like the first row and the ith column. And then you have a similar version, which is the permanent, which you may be less familiar with, which doesn't have this alternating plus or minus 1. If you're not super familiar with these polynomials, like just determinants, it's fine. Just know that these are just two polynomials that exist, and they're used all over in mathematics, like linear algebra specifically. And so the determinant has a small circuit, right? If you do your normal Gaussian elimination and you just kind of row reduce the variables, you get order n cubed size. So we can get a small circuit. But then, so that means the determinant is also in VNP, right? Because VP is a subset of VNP. That should say in. There's mistakes in this. I'm sorry. The permanent is in VNP. Just trust me on this one. That should say in, not in. My bad. But the permanent is in VNP. I'm not going to go over a proof for it because it's kind of annoying. It's a lot of tedious stuff, but just trust me, it is. But then the algebraic million-dollar question is the permanent in VP, or is it not? And it turns out that like even this VP and VNP stuff connects to like other millennium problems. If you've heard of like the Riemann hypothesis as like this famous mathematical problem that no one knows how to solve, even like all this computer science stuff connects to deep areas of mathematics. And it was shown that if VP equals VNP and the generalized Riemann hypothesis holds, a possible math problem, then a version of P versus NP holds. So this algebraic model has very real connections to our normal version of thinking about computers and programming languages. So that's kind of why people care about this algebraic model. But what can we actually do with this? Like, is there anything interesting we can do with algebraic circuits that we couldn't do with normal computers? So think about, let's just consider a bipartite graph. So we have these two sets of nodes on the left and the right, and all the edges go from left to right. There's no, like, all the nodes on the left are independent of each other, and all the nodes on the right are independent of each other. And so we could ask, can I select edges that touch every single vertex exactly once? And so here's one such selection. So notice I can't use the edge 1 to 2 because I'm already using the edge 3 to 2. And so that would use the node 2 twice. And so if I gave you such a graph, I can ask, does such a perfect matching exist? And this is like one of the most common problems in computer science. You can think of it as trying to match up preferences between people. So you can think about the left as a group of people, and you can think about the right as like jobs they have to do. People can't work on two jobs at once, but you would like everyone to be working on a job. So it's a very applicable problem. And you can imagine that as the number of nodes gets longer and longer and longer, this is a very like hard problem to do. Right? You can't, it doesn't become kind of obvious, just look at the graph and find the edges. You actually have to do some computation. And so this can be done in polynomial time. That's just kind of a fact. You see this in CS473, but it doesn't really matter how it can be done in polynomial time, but we know we can do it. But the algorithm that most people know for this problem can't be parallelized. So if you have, let's say, 20 different computers, the normal algorithm, you can't apply the computational power of all 20 computers. You can't throw new computers at the problem and get a faster algorithm. Instead, we're going to look at a new algorithm using all of this algebra that can be parallelized. And it's one of the only parallel algorithms known for this problem, and explicitly has to do with this computational stuff. So if we're going to do algebra, we need some way to construct a graph, construct a polynomial from the graph. And then so the idea is we're going to take the graph and we're going to turn it into a matrix at first. And so we're going to say that the I and jth entry in the matrix X is going to be the variable X sub ij if there's an edge between I and j in the graph and 0 otherwise. And then so we can see that vertex 1 is connected to 1, 2, and 4 on the right-hand side. So we have an x11, an x12, and an x14 in the matrix. But there's no edge from 1 to 3. So the 1, 3 entry in the matrix is 0. Right? So we have this way to take a graph and turn it into a matrix. And so now we're back to this determinant formula, and this is what's called like the Laplace expansion of the determinant. It's due to the mathematician Laplace. And there's another formulation of determinant, which is due to another mathematician, Leibniz. And it's not as well known, but it lends itself to being parallelized. And so instead of summing over and cutting out rows and columns recursively from this determinant, we can sum over all orderings of the integers 1 through n. And so we're going to have these orderings sigma. That's what that little letter is. So we sum over all orderings sigma in Sn, so the set of all orderings. And then with these orderings, we're going to get entries in, we can correspond these orderings to monomials in the summation. So like x1 sigma 1. So like if n is 3, right? And the ordering was 3, 2, 1. then x1 sigma 1 is going to be x1 3, and then x3 sigma 1 is going to be, or x3 sigma 3 is going to be x3 comma 1. So we're basically doing all possible orderings. And and for the determinant, we still have this sign. And so what is this sign? It counts how many inversions there are. So if you take two numbers, I less than j, and then sigma I is greater than sigma j, then that's an inversion. And the sign is just if the number of inversions is even or odd. I'm not going to go over the proof as to why these formulas for the determinant and permanent are equal. Just kind of believe me, they are. But the thing is, this is much more parallelizable because how many orderings are there? Well, there's n factorial. And none of the orderings kind of depend on each other. So, since none of the orderings depend on each other, I can just kind of compute it in parallel versus with the recursive formulation, I couldn't really do it in parallel because the recursive computations depend on which rows and columns I've cut out, and that can't be easily parallelized. So using this alternate formulation of the determinant, we get parallelization. And you'll notice that even in both cases, the formulas look very, very similar. Even though we said earlier that we think that the determinant is in VP and the permanent is not in VP. So one interesting thing about all of these algebraic computations is in the normal computational world, the problems that we see that are hard versus problems that are easy, they look very different. You can kind of look at a problem, and you can kind of say, oh, that looks hard. That probably isn't in, like, I don't think that would be in P. Or this problem looks easy, that's probably in P. Versus with these polynomials, they look so similar, and yet there's such stark differences in how, and like the circuit sizes that we think are necessary to compute them. So that's one of the advantages, right? There's much less difference to work with, so we can kind of hone in on small details in this algebraic world. So we have these two versions of the determinant, and this is going to allow us to have our final algorithm. So I'm going to say X is the matrix that we constructed before. So you have G, we have this matrix X that we constructed, and the polynomial we're going to look at is the determinant. And I'm going to claim that the determinant has a perfect, the determinant is non-zero if and only if X has if only if the graph has a perfect matching. And the proof isn't super interesting, so I'm not going to write it out. But the proof essentially goes along the lines of the only time we have a perfect matching is if we'd have a new ordering of all of the integers 1 through n. So those correspond exactly. So you want to look at the possible, so the determinant will only have non-zero terms if there exists a perfect matching. Every single non-zero term in the determinant would correspond to a perfect matching. And there's no cancellation that occurs. So that's kind of where the claim comes from. And a kind of a basic fact from algebra is a degree D polynomial is 0 in at most D places. So if you think about like a linear polynomial, that's 0 in at most one place. A degree 2 polynomial, a quadratic, is non-zero in at most two places, etc., etc. And this generalizes to multiple variables. And so the determinant X has degree less than or equal to n squared. Just naively, there's only n squared variables that appear. So the degree is at most n squared. And in fact, it's lower. It is, I think, just n, but n squared is easier to explain. And so we have a basic algorithm. We construct a matrix, call F our determinant. And then we're going to randomly sample n squared plus 1 distinct points. And what we're going to do is we're going to, for every point in our randomly sampled set, we're going to evaluate f at that polynomial. No, we're going to evaluate f at that point. And if it's not 0, so if f of p is not 0, then we know our polynomial, the determinant, is not 0. And so then it's true. The graph does have a perfect matching. And otherwise, we're going to return false. And that's the entire algorithm. And this is easily parallelized, like I said, versus other matching algorithms which aren't parallelizable at all. But yeah, that's it. A little bit of a shorter meeting. Hopefully everyone's staying safe in all the ice. But yeah, that's all. If you have questions, feel free to speak up or say them in the chat. And yeah, thank you.